Good morning. I wanted to share a video. I spend quite a bit of time trying to make sense of what's going on in the world of artificial intelligence. Luckily, I retired 3 years ago, so I have a lot of time to do that and have a pretty strong technical foundation to build on. But I do feel for people who are, doing full-time jobs and trying to figure out what's happening in the world. And so I thought I could help with a little bit of what I like to call sense making and making sense of what's happening in the AI world. I'll try not to overly talk about frameworks, although I think understanding all the stuff that's going on requires you to be able to recall some frameworks and continually go back to them. I'll try to keep this video, by the way, to about 15 minutes. So the three dimensions that are on this particular chart are data, model size and architecture, and compute. And those are the three fundamental resources that are driving AI progress. With data, we are concerned with the data volume and the quality. With the model size and architecture, there's a trade-off. The bigger the models get, usually the better they can perform, but they're also more expensive to run. And larger models require larger data. So there are some relationships between these constraints. And then, of course, training and inference. Inference is at runtime when you're using the model. Training is everything that happens before that, are very compute intensive. And so a lot of what we hear about in the AI news has to do with the trade-offs inherent in this particular picture. Our goal here is to develop strong general and generative AI. What does that mean? Well, strong AI meaning that it's really good at solving, very specific problems. It can perform at a very high level. General meaning that a single model can work over a wide set of tasks and domains and perform very well. So we want it to be both strong and general. And generative means we want it to be able to kind of create things, whether that be text or language or computer programs or diagrams, whatever we can ultimately find value in, we want it to be a generative capability. Important to know that in talking about these tools, we'll separate recall and reasoning. So when a model just answers a question, if you ask it a question, who was the seventh president of the United States, that type of thing, that is just based on recall if it doesn't use any outside sources. If we ask it to multiply 5 times 3, it may very well be able to recall the answer of 15. But if we give it a very complicated math problem, we expect it to write a program, to generate a program to solve that math problem. And so that would be more reasoning related. Another way to think about the distinction here is if I give you a word problem, probably remember them from school, and say something like, we're going to travel 3 days on our road trip across the United States. How long do we have to travel each day? If we average 65 miles an hour, that would be an example of a reasoning problem where it couldn't recall the answer to that, but it could construct a path of reasoning to be able to answer the question. And so we're looking for this large language model or multimodal large language model to do both recall and reasoning. We also are looking for it to do tool building, but I'll talk about that more a different day. In general, we believe there is a relationship between these three categories on the chart at the left, although we're still learning a lot. We think there's probably an optimal frontier where the marginal piece of data can't be utilized by that model size and architecture given the amount of compute we have, or there's an ideal amount of compute that we need when we have a certain model size and a certain quantity of data. So the reality of it is, though, that we haven't really found that yet. And some of the big things that have happened in the last couple weeks, DeepSeek being the one that I'm thinking of at the moment, really challenges where other people were, because with much less compute, they were able to get a very high level of performance. And, that challenges the core narrative that's out there in the world. So I recommend trying to keep this picture in your head, because it helps make sense of what we're reading in the news and hearing about on the news every day. Now, this is a pipeline picture that I've used in the past in different discussions I've done, which starts at the left-hand side. The big chunks here are the data coming in, and I'll talk a little more about that. The first phase is, let's call pre-training. That's when we kind of go through the massive amounts of data, trillions of tokens of data, if that means anything to you. And, we essentially train the model using backpropagation, which means that we are asking it to do a task. We know that the task that a lot of these models are using is just next word completion or missing word completion. And we give it feedback, and that feedback turns around and is used to improve the weights. And then we keep running the training until we get the level of performance we're looking for, and or the model seems to converge and hits its potential. After pre-training, there's often two other tasks that are done. If we have a model with like 650 billion parameters, it's going to take a long time for that to run. Most computers, can't run that, of course. And so we might do something called distillation, where we might create a 70 billion parameter model from the 650 billion parameter model. We are willing to trade off some things in terms of generality, perhaps, and other things to have a model that's more deployable. And then there's also fine-tuning, which, there's a variety of different fine-tuning mechanisms that are out there. RLHF is a big one, which just means reinforcement learning with human feedback. That's when these vendors like Google hire people, crowdsource the work or build workforces to do these type of things, to essentially give information back to the model about its preferences, kind of what they think is more readable or more believable, but also in terms of accuracy. Is the answer accurate is a very key part of that particular function. And then the last piece is what happens at inference time, which is just when you use the model. That's a big thing. 3 years ago, inference time was the efficient part of what was happening, but that's starting to change a bit. When you interact, when you provide a prompt to a large language model, what it does with that prompt after you give it the prompt is inference time. So let me quickly cover the 5 points on this page. First of all, I have to start with energy consumption. This is a big deal. Obviously, in the U.S., our energy infrastructure isn't what we would like it to be, but we're looking in the medium term of needing a huge amount of resource for our data centers. And we want it to be as clean as possible, of course. And so this is a really big focus in terms of the industry. You see partnerships with nuclear energy providers. I wouldn't be surprised if someday we see an outright acquisition of an energy company by a technology company. Jumping over to the second point, which is over on the left side of the slide, one of the exciting things that DeepSeek has done is to use extended reinforcement learning earlier in the pipeline than others did. And, while the others were certainly using reinforcement learning along the way, they were using it in a much more advanced way much earlier in the process. A lot of it was just very simply rule-based reinforcement learning, and their pipeline is really what created all this enthusiasm in the past couple weeks. Reinforcement learning is a concept where you can dig in and understand it at a lower level of detail. But essentially, it just requires a feedback signal. The feedback signal can be right or wrong. It could be preferences. It could be a whole bunch of different things. But when you think about a child learning, you often think about reinforcement learning. When they do something right, they get rewarded. When they do something wrong, they might get penalized. And that's the essence of reinforcement learning. So that's a big part of the news lately, but it's been a big part of computer science for quite a long time. We also are seeing an explosion, number 3 here, of synthetic data that's being used. Now, organic data or human data is just stuff that's naturally generated from human processes. When you're on social media and you're sending messages back and forth, that's clearly organic data. But in the last year or two, there's been a huge explosion in the use of synthetic data, which I like to think of as model-generated data. And it has a couple advantages. It certainly supplements the organic data, but it's unlimited as long as you have tools and models that can generate synthetic data. You can have as much of it as you can afford to produce. And the second piece is it can be very fit for purpose. So if you notice in your training corpus, which is what these two data sets could be called, that you've got some gaps, you might be able to generate and create synthetic data that's particularly useful inside the model. So, if you think about something like Wikipedia, that's clearly a human-generated set of information. But you could have AI write, virtual Wikipedia entries for topics that are not currently covered by the current Wikipedia, and then with some review process, enter that back in, and that would be synthetic data just verified or validated by people. So that's been a big area of focus and development. Number 4 over here is switching over to inference time. There's a lot of focus in the last 6 to 9 months on chain of thought reasoning and other things, which we knew a couple of years ago was a really promising technique. And what this means is a very extended inference time where the models are encouraged, for example, to lay out a plan of how they're going to break down and solve a problem and then follow the plan. There are algorithms that augment this, that allow it to backtrack, and that's a pretty powerful capability. When you're solving a problem as a person and you realize you're down the wrong road, you backtrack and pick a better branch, right? And so the capability to do that is very key. One of the things we're seeing that's quite fascinating is the energy consumption that this takes could be quite huge. At training time, we know we need huge amounts of compute resource, which means a lot of energy. At inference time, though, these extended inference techniques really do require a lot more computing power, and so that's presenting some challenges. I love those challenges, though, because they just create more innovation, and people will come up with architectures, including hardware architectures, that are just extremely efficient at inference time compute. The fifth thing on this slide, and the last thing I'll cover on this particular slide, is that retrieval augmented generation and grounding have been around for a while. These context windows for the models, sort of the amount of information you can provide them at inference time, are growing, and I've read up to 4 million tokens. Seems to be the absolute state of the art. Google offers 1 to 2 million tokens. Some of the smaller models, I often set my parameters to just have less than 10,000 bytes of information, and that seems to work pretty well for most of what I needed to do. So these larger context windows are, allowing us to retrieve more information. You could dump a whole book or 10 books into the window and then start asking questions. If you use tools like Notebook LM, they clearly have a huge context window that you can put a ton of information in there. What tends to happen, though, is it's not very good always at knowing what's most important and extracting the right information from all those sources. Usually the stuff earlier and later in the context window has a higher propensity to be recalled than the stuff in the middle of the context window, and people are obviously trying to fix that problem. One of the solutions is use smaller context windows, but use chain of thought, where you have some refinement of the inputs being done in early inference to create something that's more usable at final inference time. So a lot of great stuff happening there, and we're seeing lots of battles around the so-called power laws, trying to figure out, whether we can innovate ourselves to lower resource model development and model execution, and also what some of the upside constraints are there. The last thing I want to cover is just what's going on in the world of agentic AI. This is obviously everywhere now. And I think of agents as digital minions. They act on our behalf in the world, right? That's really what they do. They might be collecting information for us. They may be taking actions for us. That's, quite exciting and a little bit scary, I'm sure, for everybody as well. There's a large focus now on embodiment in AI. AI, a lot of what it learns is based on human experience, and we feed it images that we take, or we feed it text that we've written or somebody has written. And the belief is that to really kind of get to the nirvana of artificial intelligence, we need embodiment, which just means that the AI is collecting and having its own experiences. Again, a little mind-bending, but the reality of it is your kids or your dog or whatever all learn by experiencing the world, and with embodiment, that's going to be quite a powerful thing for our AI future. Quickly here, AI needs point 5 situational awareness and context. And so, for example, a lot of the model vendors now are signing deals with news vendors like the AP and the like to get news information as quickly as possible. On your Android or iPhone device, you can run a model from OpenAI now where you talk to it, and so you're speaking back and forth, but it can be using the camera at the same time and taking those images and doing things with those images, which is, when I remember to use it, is something I'm continually impressed by. If you're kind of taking pictures in a arboretum, and you want to know what a specific plant is, that AI is really good at telling you what plant that is, and can just tell you live in verbal conversation. So really powerful there. The middle here is really the heart of what was produced on the prior slide, the large language model, the multimodal large language model. It's important to keep in mind that while the kernel may be the MLLM, there's a lot of other composite algorithms and models being used in these agents. And so the composite view is probably a better one. We tend to focus on the LLMs, but it's important to know that there's a huge amount of composite modeling going on. An example of that is when you take a video and you provide it to the model, either a live video or asynchronously. The video is processed by a different algorithm, and it is fed in a representation that's useful for the MLLM. The bottom here, I don't want to forget the user, and the user provides their needs and preferences and feedback, and ultimately needs to have control over the model. And since we're able to communicate with these models in human language, the advantages and the capabilities there continue to evolve. there's also a tremendous amount of activity on the right-hand side, pun intended, I guess, that these models are increasingly able to act on our behalf. You've probably seen too many videos of people, coming up with a menu for dinner and then having the Instacart order be assembled and purchased and a delivery time scheduled and all that kind of stuff by things like OpenAI Operator and Google and others have beta offerings in this space. And one of the cool things is that these models can direct your computer maybe just through a browser and a web page, or directly with your computer if you want to give it access and do things for you. So I've started to use a program called Cursor to write software, and it will, go ahead and configure my computer so that it can run the software I'm downloading from GitHub as an example. And so increasingly I'm giving it authority to do things. It does ask for permission before it does it, but increasingly intelligent actions it's able to take. I look forward to other ones as well that we can integrate in. So, the key way to think about an agent for me anyways is that's got this sense and act cycle. It has a set of preferences and a constitution of permissible action, and increasingly they're going to do more stuff for us. So I hope that gives you some context. If you're, struggling to really understand what's going on in the world of AI, I consider myself intermediate. I don't consider myself an expert, but I'm certainly kind of, I think, past the beginner phase now. So I hope that helps.